Electric vehicles are gaining traction as they provide a more eco-friendly and sustainable option compared to gasoline-powered cars. Yet, there are still significant obstacles to overcome for EVs to become mainstream. One major issue is the expense and size of the electric motors that drive these cars. Conventional electric motors in EVs are often large and heavy, which increases the vehicle's weight and negatively impacts its range and efficiency. Moreover, these motors are costly to produce, contributing to the higher prices of many electric vehicles when compared to their gasoline counterparts. GM recognizes this challenge and has developed an innovative axial flux motor that could be the solution for creating smaller, more affordable EVs. But what exactly does this entail, and how has GM achieved it? Let's delve into this topic further. Many companies have made promises to launch electric roadsters and sports cars, but so far they have not made significant market penetration. The weight of the batteries is a major issue, but it's not the only one. Before addressing the battery weight problem, we can focus on the electric motors. Most electric vehicles today use radial flux motors. While effective, these motors are long and cylindrical, making them less suitable for the sleek design of roadsters and sports cars. Introducing axial flux motors. These compact, frisbee-like motors offer impressive power due to their unique magnetic configuration. Unlike radial motors, where the magnetic force travels perpendicular to the axis of rotation, axial motors have magnetic forces that run parallel, enabling a different, more efficient shape. Axial flux motors, much like electric vehicles themselves, have a rich history dating back to the early 1800s with Michael Faraday. However, it was Tim Woolmer who reignited the auto industry's interest in this technology. Dr. Woolmer has been dedicated to this concept for nearly 20 years, beginning with his PhD thesis. His research led to the creation of the yokeless and segmented armature axial flux motor, which has since garnered significant attention. In 2009, Dr. Woolmer founded YASA to advance this technology. The company quickly achieved industry success, securing agreements with various automakers to supply YASA motors for electric vehicles. This success culminated in YASA's acquisition by Mercedes-Benz in 2021. Dr. Woolmer's contributions to axial flux motors have been transformative, pushing this technology to the forefront of the automotive industry and shaping the future of electric vehicles. However, mass-producing these axial flux motors has been challenging, which has delayed their widespread adoption in the EV market. But thanks to persistent efforts by key companies, these motors are finally poised to make a significant impact. Traditional electric vehicles rely on radial flux motors, which function like donut-shaped electromagnets with a coiled wire stator surrounding a central rotor filled with permanent magnets. Although efficient and reliable, this design is bulky and long to generate adequate power. Axial flux motors, on the other hand, offer a revolutionary alternative, particularly for sporty electric vehicles. Picture a motor that is flat and compact, yet equally powerful. That's the brilliance of axial flux motors. Unlike radial motors, where the magnetic force spreads out like spokes on a wheel, axial flux motors have magnetic forces that flow parallel to the spin, similar to a record player. This results in a completely different and significantly more compact design. Developing these compact motors has been a significant challenge, hindering their widespread adoption in electric vehicles. However, the landscape is evolving. Companies such as General Motors are pioneering innovative designs to overcome these obstacles. One of their patents centers on a concept known as mechanical field weakening. Though it may sound complex, the principle is straightforward. Consider a car with a standard automatic transmission. When rapid acceleration is needed, the transmission delivers high torque, but the car doesn't achieve very high speeds. As the car gains speed, the transmission adjusts to offer less torque while allowing for higher speeds. This balance is known as the constant power zone. Mechanical field weakening replicates this effect in an electric motor without the need for a complex transmission system. It enables the motor to function more efficiently at higher speeds, which could lead to smaller, lighter motors with a broader range of effective power. This innovation could be transformative for compact and affordable EVs, including the sporty models many have anticipated. We've discussed the potential of mechanical field weakening to revolutionize electric motors, but how does it actually work? Let's explore this concept without delving too deeply into technical details. Picture an electric motor as a device that converts electricity into torque, twisting force, and speed. Most permanent magnet motors inherently balance these two factors. High torque provides powerful acceleration but limits top speed. Conversely, reaching high speeds requires sacrificing some pulling power. This trade-off is often visualized as a bell curve, with an optimal point in the middle, where both torque and speed are balanced. This optimal point is the constant power zone. It's akin to having a car that can quickly accelerate and still achieve high speeds without frequent gear shifts. Historically, optimizing electric motors required complex software and electronic controls known as inverters. Although effective, this method can lead to inefficiencies and energy loss. This is where mechanical field weakening offers a solution. Consider it similar to adjusting the distance between the engine and the wheels in a traditional car. In an electric motor, this is done by physically altering the gap between the stator, the stationary component with coils, and the rotor, the rotating part with magnets. Picture the stator as a magnet and the rotor as a piece of metal. When they are close together, the magnetic pull is strong, resulting in high torque but lower speeds. By increasing the distance, the magnetic pull weakens, reducing torque but enabling the rotor to spin faster with less resistance. It's like changing gears, but without the complexity of a transmission system. This adjustment changes the motor's operating range to match the required performance: high torque for acceleration or higher speeds for cruising. This method provides several benefits. Firstly, it offers a more straightforward and intuitive way to achieve the constant power zone. Secondly, it can be more efficient than relying solely on electronic controls. This efficiency is especially important in places like Japan, where electric car enthusiasts compete in econo-power races to maximize efficiency. By using mechanical field weakening, these racers can optimize performance and gain a competitive edge. The theory of mechanical field weakening in axial flux motors is simpler, but it comes with unique challenges. Axial flux motors consist of two opposing disks with an air gap between them. When activated, these disks spin and exert a magnetic force that pulls them together. At high torque levels, this force becomes very strong. Usually, a fixed bearing keeps them apart, but with mechanical field weakening, the rotor and stator need to move axially to adjust the air gap while remaining stable in their new positions. General Motors proposes addressing this issue with a hydraulic system, which seems practical. Using hydraulic fluid, the gap can be narrowed to boost torque and reduce speed, or widened to lower torque and increase speed. Although this approach may add cost and complexity, it's essential to consider the advancements in automatic transmission technologies. Compared to those, implementing mechanical field weakening in axial flux motors is relatively simpler and has promising implications for smaller, lower voltage electric vehicles. This technology could provide sufficient torque for acceleration and then widen the air gap to achieve higher speeds, making smaller and lighter motors more practical. A chart from the patent illustrates how available torque decreases, but the range at which it can be applied expands. It's fascinating to consider the potential of a system that functions like a continuously variable transmission, CVT, for electric vehicle motors. Continuously adjusting the air gap to adapt the motor's characteristics to different scenarios is quite innovative. Despite its potential, this technology may not be available immediately. The next generation of mass-market electric vehicles will likely focus on advanced battery technologies and minor enhancements to radial flux motors. However, the investment of a company like GM in axial flux technology suggests a promising future. What are your thoughts on this? Share your opinions in the comments section.